Okay, yeah, so this talk is going to be based on joint work with one of my advisors, Pravesh Kothari, who used to be a professor here but has since moved to the IAS in Princeton. Yeah, so let me start off the talk by just defining locally correctable codes, because that's going to be what this talk is about. And so locally correctable code is just going to be a type of error correcting code, meaning it's going to give you a map that takes a k-bit message B and maps it into an n-bit string X. Okay, and for this purpose of this talk, I'm going to assume that all our codes are systematic, which means that the first k bits of this encoded string X are actually just the original message. Okay, so I've highlighted that in blue. And we're going to be working over the standard model of adversarial errors. So that means that we're going to then allow an adversary to come in and make delta n, or introduce delta n errors into the encoded string X to produce some new corrupted string Y. And what we want is for the code to be locally correctable, which means that we want to be able to recover any bit of this encoded string X by only reading a few bits of the corrupted string Y. And so more formally, we're going to want there to be some decoding algorithm that will take as input the index U that specifies what bit of the encoded string X we wish to recover. And then the decoder gets to toss some coins and then read at most Q entries of the string Y. This can be done adaptively, meaning that the decoder could make one query, then see the answer, and then decide what location to read next based on the answer that it sees. And then at the end, the decoder gets to output some x hat sub u, which is hopefully equal to the true bit x sub u that we're trying to recover. Okay? And more formally, we'll just say that their code is q delta epsilon locally correctable if for any code word x and any y within delta n distance of x, and for any u, the decoder will read at most q bits of y and succeed in recovering x sub u with probability at least 1 minus epsilon. So there's three parameters here. There's q, the query budget of the decoder, delta, the proximity parameter, which is how close y needs to be to x, and then finally there's epsilon, which is the error probability of the decoder in the presence of delta n errors. So locally correctable codes are very, very useful objects. I mean, they have a whole host of applications. They were introduced in some early works on program checking and probabilistically checkable proofs, and they also have applications to cryptography and things like private information retrieval, and so on. So they have a lot of applications. You've probably seen these objects if you've seen a proof of the PCP theorem and so on. So I'm not going to spend too much time on motivation, but if you take a graduate complexity theory class or something like this, you'll see these objects come up pretty frequently. So I've defined locally correctable codes, and now what I want to do is define a related notion called locally decodable codes, because there's another notion that's also been studied quite a bit that just has a lot of very similar properties. So locally decodable code is almost the same as a locally correctable code. The difference is here we only care about recovering bits b sub I of the message rather than recovering the whole string, right? So here we're going to say the input now is going to be some index I and k, which specifies the bit b sub I that we wish to recover. Right, so I can kind of toggle back and forth, and on local correction, you see I'm trying to recover each x sub u of the encoded string, whereas on local decodability, I only care about recovering the bits of the message. Okay? So, quick quiz. Can anyone tell me which of these notions is the stronger notion? Like, does local correction imply local decodability, or does local decodability imply local correction, or are they incomparable? Any votes?
Local decodability is stronger.
Local decodability is stronger.
I think local correctability is stronger.
Yeah, local correctability is stronger. Ryan.
Just trying to make it exciting.
Okay, fine. Yeah, so local correction is stronger, and the reason is pretty simple. So here I have my whole encoded string, and I need to be able to recover any bit of the encoded string, but in particular, I have to recover the first k bits, which are the message, right? So if I can locally correct even the first k bits, that's just local decodability, and local correctability is a stronger thing where I need to be able to correct all n bits. Okay? So the first question I want to ask is, do these objects even exist? Now, this is a little bit silly because, of course, these objects are going to exist. Otherwise, I would not be up here talking about them. But I want to point out that this is a somewhat non-trivial problem already on its own. And by existence, I mean a purely combinatorial problem where I just want to show existentially that one of these codes is out there. In particular, I don't care about things like efficient constructions or efficient encoding maps and things like this. And the reason this is somewhat challenging already compared to, say, standard models of error correction like channel coding and so on is for channel coding, Shannon's original proof just proves that like a random code is a good code, whereas here there's no natural random model to sample these codes from, so you can't apply things like the probabilistic method to give constructions, or to prove existence, rather. So already this is somewhat non-trivial, but I mean, these codes do exist, and there's in fact a very simple way to construct them, which is the Reed-Muller codes. So these are some of the earliest error-correcting codes that people ever came up with, and they give you a very simple Q-query locally correctable code with block length n, the length of the encoding, that's exponential in k to the 1 over q minus 1, where k is, remember, the number of bits in the message. So let me just walk you through this construction for q equals 3, and you can imagine how to generalize this to larger q. It'll be pretty straightforward. Q is the number of queries of the decoder, yeah. Good. So here's the construction. I think of my message as giving me coefficients of a degree 2 polynomial f in t variables over some small finite field, like say f4. And then my encoding is to simply evaluate this polynomial over the whole domain. Okay, so that gives me a way to encode my string b into some message with length 4 to the t. And so the only thing I really need to tell you now is how do I decode? How do I do my local decoding? So let's say I want to correct the bit, the zth bit in f of z, right? So what am I going to do? Well, it's pretty straightforward. I'm just going to pass a random line through z. The line has 4 points because we're working over f4, and I'm just going to query the 3 points on the line that are not z. Okay, and because this is a degree 2 polynomial and have its evaluations at 3 points on the line, I can interpolate and get its value here. So the key property that this decoder has is that the distribution of one of these points individually on this line is uniform over the whole domain f4 to the t. And what this means is that if I have delta fraction of errors, the probability that, say, this point here is one of those error points is delta. And so the probability that one of these points is corrupted is at most 3 delta. So with probability 1 minus 3 delta, all these points are uncorrupted, and then I successfully recover f of z. Right? So I can, with some small fraction of errors, I can recover with high probability. So this gives 3 LCC over f4. And I can get a binary code just by projecting down with the trace map to f2. And if I just compute the parameters, we'll see that k is about t squared over 2. That's the number of coefficients in this polynomial. And n is set as 4 to the t, where if you compute the constant, it's like 2 to the 2 root 2k. Okay, so that's exactly exponential and k to the 1 over 1/2. Right? So this is a very simple construction. And the question I want to investigate in the remainder of the talk is very simple. Just, can we do better? So again, this is like a very simple construction. It's perhaps one of the first codes you would even come up with. And it's based on some very simple algebraic techniques of just low-degree polynomials and interpolation. And you can imagine that if you used more sophisticated algebraic tools, you could potentially do better. So what I want to do now is wind the clock back 2 years and tell you all the stuff that we knew about this problem as late as in 2022. So what I'm going to do here is I'm going to, well, I mean, if you want to investigate if you can do better than Reed-Muller codes, you should probably just start setting values of q. So you could try setting, say, q equals 1. Turns out one-query codes don't really make much sense. So the first non-trivial setting of q is q equals 2. And here, if you just look at this formula, the block length of the code is 2 to the k, and it gives you a linear 2-query locally correctable code. I guess I didn't define a linear code, but a linear code just means the encoding map is a linear function, and therefore the set of code words is a linear subspace over f2. So this is a pretty bad code. I mean, we're encoding k bits into a string of length 2 to the k. So it's not very efficient, but it turns out that this is tight. There were some works in the early 2000s on proving lower bounds for this weaker notion of local decodability. And they prove that you, in fact, need a block length that's exponential in k, so up to a constant factor in the exponent, this is indeed tight. So for q equals 3, as I said, we have this construction for Reed-Muller codes that is block length 2 to the 2 square root 2k. And it turns out that for the weaker notion of local decodability, you can actually do much better. There are some works by Sergei Yakanin and Klim Efremenko that construct matching vector codes, which are a family of codes that give you, in particular, a linear 3-query locally decodable code where the block length is 2 to the 2 to the root log k log log k. So this is a strange function here, but let me just interpret it a bit for you. So remember, the square root k up here is 2 to the 1/2 log k, right? So this is 2 to the square root log k, which is in particular smaller than any polynomial in k. So this is subexponential in k. So it's much, much better than Reed-Muller codes. And you might wonder if perhaps this code is, in addition to being locally decodable, is also locally correctable. And it turns out this is actually an open question. And this is in spite of the fact that this is like a very explicit code. So you could imagine that for an explicit code, it's pretty easy to rule out that it's locally correctable. It turns out that for this code, that's actually not the case. And I guess, moreover, it's believed that this code is not locally correctable because this local correction property is a pretty strong property. So if it's not baked into the original construction of the code that you have, your code is unlikely to have this property. But nonetheless, this is something we've been unable to prove. And so these are the two best constructions as of 2022 for 3 LCCs and 3 LDCs. And you could wonder how tight these constructions are. And the answer is we really just have no idea. The best lower bound we have is this very weak n is at least k squared lower bound for 3-query locally decodable codes. And this comes from this work of Karenides and de Wolf that also did these 2 LDC lower bounds as well. And in spite of the fact that this lower bound is rather weak, I mean, this is k squared. It's not even like k cubed, right? So it's polynomial. These things are much larger than any polynomial. We have some evidence that our techniques for proving these lower bounds cannot even go beyond this k squared barrier. So just to summarize, I asked, can we do better than Reed-Muller codes for 3-query locally correctable codes? And the answer is yes for locally decodable codes, and for local correction, we don't know. And at this point, these codes have been studied for about 30 years or more, and people have tried reasonably hard to get better constructions. So you might, at this point, it could perhaps be reasonable to conjecture that we're not getting better constructions than Reed-Muller codes because there are no better constructions. That is that Reed-Muller codes are simply optimal locally correctable codes. And we actually know that this is true, at least when q equals 2. We have a proof. And for q greater than 2, this is wide open. And moreover, there's a very interesting barrier to proving this conjecture, which is a connection to design theory uncovered in this work of Barkol, Ishain, and Weinreb that basically shows that this Hamada conjecture from design theory, essentially when you rephrase it in the language of locally correctable codes, just says that it conjectures that Reed-Muller codes are optimal design LCCs, which is a specific type of linear locally correctable code with some additional nice structure. So in particular, if you want to prove this conjecture, you have to prove this conjecture, and this conjecture is pretty wide open also. And there's one more barrier, which is that all our lower bound techniques apply to this weaker notion of locally decodable codes. And as I told you, there are better locally decodable codes than Reed-Muller codes. So you can't prove this conjecture if you're only proving lower bounds for locally decodable codes. Okay, so this is pretty much the whole story as of 2022. Okay, and now what I want to do is tell you all the progress we've made in the last 2 years on this problem. So I'm going to plot results by having this graph down here, where here we have the best lower bound of k squared, and here we have the best upper bound of 2 to the 2 square root 2k. And in the middle, I have this LDC barrier. This is the barrier you cannot go beyond if you're proving lower bounds for locally decodable codes. And down here, we have this k squared barrier, this somewhat technical barrier that it seems like our techniques cannot go beyond. And so in first work, we proved also, this is joint with, I guess, my other advisor, Venkat Guruswamy, and one of his students, Omar Al-Rabia, we proved that 3-query locally decodable codes have a block length that's k cubed. Okay, so this is a nice small improvement, but in particular, it goes beyond this k squared barrier that seemed like our techniques were unable to go beyond. And then recently, Pravesh and I proved that for linear 3-query locally correctable codes, they must have a block length n that's 2 to the k to the 1/8. So that is way up here. In particular, it's actually beyond this LDC barrier. And as a result, our techniques do not work for locally decodable codes. And this is kind of obviously inherent if we're going to go beyond this LDC barrier. Moreover, this is actually the first lower bound proven for any locally correctable code over the binary alphabet that does something that is different for the case of locally correctable codes as compared to locally decodable codes. Because you can always prove a lower bound for locally correctable codes by just pretending that they're locally decodable codes and working with a locally decodable code. But here, if you want to prove such a lower bound, you can't do this, and this is essentially the first lower bound that even gets any difference between LCCs and LDCs. Another byproduct is we prove that matching vector codes are not locally correctable codes, which was something widely believed but formally not known. And we also separate these notions of locally decodable codes and locally correctable codes over 3 queries. We prove that there's a construction of a locally decodable code that's better than the best possible locally correctable code. And I should point out that for q equals 2, such a separation is actually impossible. We have the best construction of a locally decodable code, and it's also locally correctable. So you can't prove such a separation. So something interesting is happening at q equals 3.
Can you also prove lower bound for LCCs which aren't systematic?
So a linear code is always systematic. Yeah. You just sort of pick your basis. Like there's going to be k linearly independent elements in the, yeah. Exactly. You can also turn a nonlinear code into a systematic one with some small loss in parameters. It's not actually that big of a deal. So it's essentially without loss of generality. Yeah. So, I mean, we posted this paper, I guess, late last year, and as early as February, Tal Yankovitz, a PhD student of Gil Cohen, improved this all the way up to a 2 to the k to the 1/4. And he essentially followed the same proof using similar ideas, but then he incorporated some of his own clever new tricks to get this up to a k to the 1/4. And then very, very recently, a work of Omar and Venkat gets this all the way up to a 2 to the square root k over log k, which is almost optimal, right? Because this is a square root k, so it's up to this log k factor. This is optimal. And their proof incorporates essentially the same core technical idea, but the execution is going to be a bit different from our strategy. And in particular, they use this connection to this rainbow cycle problem, which is a problem studied in combinatorics. This connection was something that we had perhaps implicitly observed already in our original work on LDC lower bounds, and there's a connection made explicit in this work of Shea, Kotari, Mohanty, Munha, and Sudakov. By the way, Shea is our Tim Shea, who's a PhD student here. And when they go through this connection, they then apply this breakthrough result on the rainbow cycle bound of Alon, Buchit, Sauermann, Zakharov, and Zamir, and they use that to get their lower bound. And if you rephrase our proof, or reinterpret our proof using this connection to rainbow cycles, we're essentially proving some weaker form of this ABSZZ result. We're proving the existence of some weaker form of a rainbow cycle, whereas here they're proving the existence of some stronger form. Okay? And concurrently, Pravesh and I proved that, at least in the case of design LCCs, which is a special case of linear LCCs, they have a block length that's 2 to the, well, up to this little over 1 factor, just root k. So I'm not hiding any constant in the exponent here. Okay, so up to this 2 root 2 factor, this is tight. In particular, this proves this Hamada's conjecture for 4 designs up to this 2 root 2 factor. And what I want to point out here is that this log k factor loss in this proof comes from some extra loss in the rainbow cycle bound. Now, this extra loss in the rainbow cycle bound was initially believed to not be necessary, but this work of ABSZZ is actually starting to speculate that perhaps it is necessary. And what that means is that if their speculation is true, getting this lower bound all the way up to the tight answer of square root k will require the fact that our proof here is only showing the existence of some weaker notion of cycle rather than the stronger notion of rainbow cycle. Okay? But in any case, all these lower bounds are for linear codes only, with the exception of this first weak k-cubed lower bound, which holds for not just LCCs, but also LDCs and even nonlinear ones. So in particular, if you care about nonlinear locally correctable codes, our best lower bound is still just this k-cubed. And so in the same paper, Pravesh and I proved some better lower bounds for nonlinear codes. Namely, we get this k to the 1 over 2 epsilon lower bound, where epsilon is this error probability of the decoder, which you should think of as like some small constant. So epsilon is something like 1 over 100. You know, we've far surpassed this k-cubed bound. And as epsilon goes to 0, we get this all the way up to a k to the log k. So something super polynomial in k. It's not exponential. It's not going beyond this LDC barrier here, but it's much, much better than the k squared that we had just a few years ago. So is the landscape of the results clear? Maybe this is a good time to pause.
All the results that I mentioned, epsilon, delta, for
So yeah, I think of epsilon and delta as like small constants. So here they would appear somewhere like next to k in the exponent. I think it's actually like a delta squared in pretty much all of them. So it'd be like replace k with delta squared k. But for linear codes, epsilon is, well, so there's some weird.
and then in the designs, there's no epsilon.
Yeah, delta is actually 1/3. It's a perfect matching in a design. Yeah, so there's no delta also. Epsilon here, there's some weird definition issues where, and for nonlinear codes, epsilon and delta are kind of coupled because delta is the number of errors and then epsilon is the error probability in the presence of that fraction of errors. So what we really do to take epsilon to 0 while keeping delta like non-zero is we look at this other notion of smoothed codes. And there the parameters epsilon and delta are decoupled, and then epsilon is like the error probability in the presence of no errors. So then for linear codes, when there's no errors, it always is correct. And then here for nonlinear codes, if you assume that it's always correct where there's no errors, you can get like something super polynomial. More questions? Okay. So for the remainder of the talk, what I'm going to do is tell you a bit about the proof of this exponential lower bound here. Because pretty much all the other proofs essentially are incorporating like the same ideas. Okay, so here's the strategy. We're going to borrow this approach that we had in our previous work, where we're going to reduce the task of proving these lower bounds to certifying unsatisfiability of a specific class of XOR formulas, which are systems of linear equations mod 2, and these formulas will have some minimal amount of randomness in them. What you should view these formulas as doing is the following. I'm going to pick a decoding algorithm. I can just kind of choose one arbitrarily. And then what I'm going to do is prove that for that decoding algorithm, there is no way to encode the message such that the decoder succeeds. And that's what this constraint satisfaction problem encodes, that the fact that the decoder should succeed in decoding the message when given a valid code word. And then we just argue that for a random message, there is no valid encoding that will satisfy the CSP, and therefore there is no code. And so to prove unsatisfiability of these XOR formulas, what we're going to do is use some tools we developed for building algorithms for refuting or certifying unsatisfiability of semi-random CSPs, which are CSPs with minimal amount of randomness in them. So here there's minimal randomness. Here there's also minimal randomness. It turns out that, well, the minimal randomness, the type of randomness is quite a bit different in these two settings, but nonetheless the tools are sufficiently general here that we can still use them to make this strategy work. Okay? And so I guess the application of this algorithm is not a black box application, but nonetheless the tools are general enough that the approach goes through. And I want you to view this as a sort of theory analog of the strategy that Bernardo told you about just a few talks ago, where what he did was he proved theorems by basically encoding them as SAT formulas and then running his SAT solver on his computer to learn the answer, right? And so here we're doing some sort of theory analog of this because unlike Bernardo's setting where he has like a very concrete problem, here the collection of XOR formulas that we consider are an infinite family of asymptotically large instances, so it's not like something you could just put into your computer. But nonetheless, the high-level approach is indeed inspired by the approach that Bernardo uses in his work. So this is the way I like to view the proof. This is the way I have all the intuition for the proof. But for today, I'm actually going to present the ideas as a reduction from a 3-query locally correctable code to a 2-query locally decodable code. And then once you have such a reduction, you can apply a lower bound for 2 LDCs to get your final lower bound. And the reason I'm going to present it like this is that it gets rid of some of the notational baggage of introducing CSP refutation and things like this. But I think, all the intuition I have for the proof really comes from this approach.
Does it get the same?
Yeah, it's the same. Well, it turns out actually for linear codes, when you do it this way, you can save like a couple extra log factors. But it's perhaps more of a deficiency in our proof rather than anything real, because if we were to get the square root k optimal bound for linear codes, you would also get it with the refutation. It like loses some extra log factor because some parameters squared. Yeah. Anyways, okay. So let me move on to this reduction, but I guess before I can do that, I have to first tell you some more standard or combinatorial form that LCCs have. So the way I want to motivate this is I want to think about what the decoder should be doing when it tries to decode x sub u, right? So what's it going to do? Well, it kind of has only two things it can do. It's first going to query some set of entries of y. So these are the entries it reads. And then it's going to output some predicate on the entries that it reads to get x sub u. Like what else can it really be doing? Okay? And so for linear codes, it could be adaptive. For linear codes, they are never adaptive. Yeah. For linear codes, they don't have to be adaptive. Yeah, so for linear codes, first off, yeah, it's always going to be non-adaptive. This is non-adaptive, right, because the entries, the queries I'm making don't depend on the answers to the previous queries. But yeah, so for linear codes, the predicate can be assumed to be linear. This kind of makes sense because the code is linear. So that means we're just going to output the parity of the bits that were read by the decoder. And the other property we want to have is that these query sets C should be somewhat evenly spread out across the whole code word. Because if they're concentrated in a particular subsection of the code, then you could imagine that that part of the code is always corrupted. That's like the corrupted part of y. And in that case, you're not going to be able to recover x sub u at all. I mean, that part of the code could just be noise, and then there's no information encoded about x sub u or even the message b in that part of the code, right? So these query sets C have to be somewhat evenly spread across the whole encoded string. And the way we formalize this is we show that there exists, these query sets have to form what's called a 3-uniform hypergraph matching. So there's going to be one of these matchings, h sub u, per bit x sub u in the encoded string. So what do I mean by a 3-uniform matching? What it means is these C's are disjoint, and they all have size exactly 3. And there should be omega n of them. So just to visualize this here imagine this is my encoded string, and these are 4 hyperedges in the matching. And then here I've colored the bits depending on which hypergraph or hyperedge they're in. Okay? So each hyperedge gets exactly 3 bits assigned. They cover some constant fraction of the total code word. And there could be some bits that are not in any hyperedge because it's not a perfect matching, but nonetheless a constant fraction of these vertices are in some hyperedge. Okay? And so what the decoder is going to do is, without loss of generality, we can assume that such an HU exists, and the decoder simply just picks a uniformly random hyperedge. Let's say it picks the C1, and then it will read 0, 1, 0, and then output the XOR, which is 1. Okay? So it's a very simple structure. Another way to view this is by saying I'm specifying the parity check matrix of the code, and I'm saying it has a 4-sparse parity check matrix, where basically what I do is for each choice of this u and each c in h sub u, I get the equation xv1 plus xv2 plus xv3 equals x sub u for all code words x. So you can think of the code as being defined by these hypergraphs h sub u, and then my code is simply the set of vectors x that satisfy all these equations when I put them together. And then k is the dimension of the subspace, which is like the dimension of the kernel of this matrix when I fill in the entries appropriately. Okay? Are we all happy with this definition here?
So some of these constraints, I guess if you fix a single u, they're probably not redundant because disjointness. But if you have to put them all...
Yeah, they have to be extremely redundant.
Yeah.
Like, we can count how many constraints do I have. I have omega n of them per u.
Yeah.
So I have like n squared constraints and n variables. So they have to be extremely redundant. Otherwise, you will, like if these hypergraphs are random, you have like no dimension. Right? The only thing that will satisfy them is the zero, all zeros code word. Yeah. This is sort of, by the way, why locally correctable codes have to have all this algebraic structure, because that's like sort of the only way we have to generate large systems of linear equations that have non-trivial solutions. Good. Okay, so now let's maybe move on to this reduction. So we start off with this parity check matrix, which are these hypergraphs h1 through hn. These are 3 uniform hypergraph matchings. And our goal is to construct a 2-query locally decodable code of some slightly larger length, like n to the order L, where L is going to be a parameter that I will pick. And then we can apply our 2 LDC lower bound, which implies that the dimension of the code, which is k, the number of bits in the message, is at most L log n. Okay? So what I'm going to do is I'm going to define my 2 LDC by giving you a transformation that will take a code word in the LCC and produce the corresponding code word in the LDC. And it's going to be very, very simple. So I'm going to take code word x, and I'm going to map it to a string y in this 0, 1 to the big N, where big N is n choose L, where L is, it's the same L here. This is the parameter that I will choose. And, well, when I think of it like this, I can identify this big N with the set, or the collection of sets, subsets of n of size exactly L. And when I do that, it's kind of obvious that I should set y sub s to just be the sum of v and s of x sub v. This is sometimes called like the direct sum encoding. This is a very, very simple lift of x to this larger space. Okay? So I haven't really done anything so far. The real hard part of the proof is proving that this collection of code words y indeed forms a 2-query locally decodable code. Right? So that's the hard part. And just by analogy to what I already argued for 3 LCCs, this is going to be a 2-query locally decodable code if I can find matchings. These are matchings on graphs now, where the graph has got vertices of big N vertices for each of these choices of s. And we want these matchings, one for each u, to have size omega n, and should be such that for each edge, st, in the youth matching edge sub u, this y should satisfy ys plus yt equals x sub u for all code words x. That is, we can think of this as the locally decodable code where s and t are my queries to decode x sub u. And so this tells me that when I query s and t and read y sub s and y sub t, I should indeed get x sub u back. Okay? Is the goal clear?
Could you say this?
Yeah. So these matchings have edges. And you can think of the edges as like telling the potential query sets, right? So when I want to decode x sub u, what I'll do is I'll pick an s and t in this matching. I'll query s and t, and I'll read y sub s and y sub t. And what this condition is saying is that when I read y sub s and y sub t and I add them together, I do get back x sub u.
Sorry, the code words that you're querying, shouldn't they be y's instead of x's if you're talking about the LDC?
This is uncorrupted. There's no corruptions. If you have a large matching, then like let's say this matching has like n over 100 edges. If you corrupt n over 1,000 vertices, then like most of your edges are still uncorrupted. Yeah. So you had a question?
Essentially the same question.
Okay. Yeah, so there's no corruptions anymore. Like if you just find large enough matchings, the fact that the query sets are spread out means that when you introduce errors, you can't corrupt too many of the edges. Yeah. That's the intuition for wanting them to be spread out.
So here y is like a function of x.
Y is a function of x, yes. So I pick my code word x, and then I like lift it to this y, and then, yeah. Good. Okay. So what we're going to do is we're going to define a graph, where the graph has edges s and t if y sub s plus y sub t is equal to x sub u for all code words x. Essentially, we just look at these equations, and you can think of all the equations that you could derive in the span of these original parity check equations that we have. And then we'll add an edge st if we get one of those equations. And then what I want to argue is that this graph has a large matching m sub u. And very clearly for this to happen, this graph needs to have large average degree. Because if its average degree is smaller than like some constant, there just are simply not enough edges in the graph for it to have a large matching. Like even if the matching contained every single edge in the graph, you just simply do not have enough edges to have a large matching. So the graph clearly needs to have large average degree. The second thing is if the graph actually has bounded max degree, meaning its max degree is some constant times the average, then if I just form my matching greedily, I will actually recover a matching of size omega n. This is basically I just pick an edge while there's a vertex that's unmatched and has an edge to another vertex that's unmatched. I just add it to the matching and just keep going. Okay. The thing is, this is going to be false. So this will turn out to be something that's false, that's kind of inherent to this direct sum encoding. So we're going to need to do something different. And so the main technical part of the proof is we argue this row pruning step, where what we do is we find a dense subgraph of this graph G sub u that does have bounded max degree. And so if we can find a subgraph G prime sub u that has roughly the same average degree, but now has the bounded max degree, then I can find a large matching in G prime, and therefore also this matching is in G, and I'm done. So these are essentially the two parts of the proof. This first step is some intuition that tells us that we actually have the possibility for a proof to go through. And the second step is the main technical part that proves that it actually works.
Is it a big disaster if the maximum degree is like logarithmic?
Not a huge disaster, no. Because you lose some like log n here and you lose some extra log n here. Yeah.
But anyway, you're going to get it down to a constant factor in part 2. So.
Yeah. Yeah, we'll get it down to a constant factor.
But like, this is false part. It could be like super false.
It's super false. No, it's like very, very easy to construct a vertex that has extremely high degree. Yeah. But these vertices are very, very rare. So you can kind of just like throw them all out and then your graph is actually fine. Yeah. Okay, so let's talk a bit about step 1, showing that the graph has large average degree. And by the way, the average degree is going to depend on the parameter L. So essentially, we're going to set L such that the average degree is at least some constant. And then that will tell us the lower bound that we get. Okay? So we're going to call this the degree heuristic, which is giving us some intuition of the potential best lower bound we can prove. So let's look at this graph a bit more. I said I'm putting an edge connecting S and T if, well, y sub s plus y sub t is equal to x sub u for all code words, but that means just that sum v in s, xv, plus sum v in t, xv, is equal to xu, right? And if I just observe that if v appears in both s and t, then xv is going to cancel with itself. So I'll be left with just the sum of vertices in the symmetric difference, which is the set of vertices that appear in s or t, but not both. And in this way, I can view each of these edges as being labeled by a set R. Now, the set R is simply the symmetric difference of S and T. And essentially, if I have an equation, sum of V in R of xv equals xu, this produces a bunch of edges in my graph. So it produces many, many, many edges, simply corresponding to pairs S and T, which have symmetric difference R. So the way I can think of this graph is I really just figure out some equations that have x sub u on the right-hand side, and then I look at those equations, and I see how many edges it produces. Okay, and then I want to count like the number of equations times the number of edges produced per equation.
So x is like a code word
Yes.
of the original
Yes.
LCC, right?
Yes.
So this is looking for some, this is basically redundancies among the
Yes.
code words.
Yes.
Short redundancies. Okay.
Maybe not short. Size of R, I have not specified size of R. Yeah. You should think of them as short-ish. Good. So I can count the number of edges produced by a particular R. And it turns out it produces like capital N times L over N to the size of R over 2 edges. So the number of edges it produces goes down as the size of R increases. That's perhaps somewhat intuitive. In particular, it contributes this amount to the average degree or the density of the graph. Now, I'm lying a little bit in that this is not true if the size of R is odd for some rather annoying technical reasons, but it turns out you can define a related graph that's more complicated that will also handle the case when the size of R is odd. So I'm just going to sweep that under the rug for this talk. Okay? But in any case, we have this trade-off, right? Pick an equation, a size of R, I get this many edges. So I need to count. How many equations do I have? And there's a very simple way to do this. We can just recall the equations we started with. Namely, for each u, I have this whole hypergraph H sub u, right? And this has these equations of exactly this form for each c, hyperedge c. They have size 3, and I have omega n of them. So what do? I can just see how many edges I got, right? So I get L over n to the 3/2 times omega n, which tells us our average degree is this, which needs to be at least 1. And so if I just rearrange, I'll get that L has to be n to the 1/3. And so this tells us our potential lower bound is something like k is at most n to the 1/3. And this is actually the calculation that leads to the full proof that gives us this cubic lower bound for locally decodable codes. And the reason this is applying for locally decodable codes is I'm only using one of the hypergraphs here. I'm using the h sub u, whereas for locally correctable codes, the difference is I really have n of these hypergraphs, and somehow if I want to do something different for locally correctable codes, I need to make use of all n of these hypergraphs simultaneously in some way. So the way we're going to do this is we're going to argue that there are many, many derived constraints where size of r is larger than 3. Okay, so we're going to increase the arity a bit, but so when we increase the arity, that's going to lower the number of edges produced per r, but we're going to produce so many more equations that it's going to balance out and actually break in our favor, and we'll get a better lower bound. Okay? So that's what I'm going to tell you about next. So how do we derive constraints? Well, we're going to do it in a pretty intuitive way. So I'm going to start with a constraint that looks like this. I'm going to write it in this form. So I pick xu, and I have c, so hyperedge, and hu. And I'm going to think of one of these variables, which I'm going to call w, to be chosen to be special arbitrarily. And I have this equation. Okay? Then what I'm going to do is I'm going to take another equation, but now from hw. So it's an equation with xw on the right-hand side. Right? So xv3 plus xv4 plus xw prime equals x sub w. And now I'm just going to add them together. Okay? So now I have, well, clearly arity 5, because I have these 5 variables that are uncancelled, and w cancelled with itself. Right? So the arity has gone up, but let's now count how many equations I have. So here I have omega n choices of this hyperedge, and then 3 choices for my special vertex w. And then once I have fixed w, I again get omega n choices here. Right? So I have about n squared total constraints. So now we can plug this into this degree calculation and see if we win. Right? So it produces some number of edges. If I rearrange, my average degree is L to the 2.5 divided by square root n. And then this turns out I can take L to be n to the 1/5, which means my lower bound will look something like k to the 5 is at most n. So this has given us some small win. We've beaten k cubed by just doing this very simple process. I mean, this isn't a full proof, but it's like some intuition that this is going to help, right?
So do you think of like the first C?
Yeah.
Do you also think of that constraint being an HW?
It's not necessarily an HW. This is like one of the annoying things about, general linear codes. For designs, it is. It has this kind of reflexive structure, but it's not necessarily there. This is actually kind of something that causes the biggest technical headache in the proof. Okay, so this is a very simple one-step process. We got some small win. You can imagine if I just keep going, I will win more and more. And so that's what we do. We form longer chains. We just keep going, keep tacking on more and more constraints in this form. And we produce constraints of arity 2r plus 1, but we produce omega n to the r of them. Okay, so we produce the constraints are growing in arity, but we get a lot of them. And the arity is always odd, which is a little bit annoying. But you can compute the arity by saying that each one of these links in the chain has 2 uncancelled blue variables, and then the last one has this extra red variable, which is where we would hook on the next link in the chain if we were to keep going. And so this is always odd. The fact that it's always odd causes, again, a lot of technical headaches, which I'm going to sweep under the rug. But okay, I mean, it's always odd. We just kind of have to deal with it, and we're going to have to work hard to make this work. But in any case, I can go through this edge density calculation. And the average degree is going to be something like L to the R over square root n. And this now says that I can potentially take L to be as small as n to the 1 over 2r. Okay? And, well, now what should I set r to be? Well, I kind of want to set r to be something like log n, right? So this will be a constant. And that's what we'll do. It turns out there are some extraneous log factors that prevent you from taking L to be as small as a constant. So in the end, we ended up with this log to the 8, which gives us this big win, gives us this exponential lower bound. Okay. Okay, so this is essentially this first part where I argued that now the graph has large average degree because I simply form these chains, consider only the edges coming from these chain constraints, and I've argued that that has given me enough edges so that my density is large, right? So then the main technical part of the proof is arguing that this graph indeed contains a large matching, or rather that it has a dense subgraph of bounded max degree, which then implies that it has a large matching. Okay, so this is the row pruning step, as we call it, because we're essentially pruning off rows of the adjacency matrix of the graph. And the key idea is we're going to argue that if we pick a random vertex in this graph, with high probability it has degree that's like some constant times d sub u. And the key thing here is that when we switch to this probabilistic viewpoint, we can apply things like concentration bounds that will be very, very nice and allow us to bound this sort of quantity. And if we get this high probability to be high enough, then if I just throw out all vertices of larger degree, there are not very many of them, and in particular, you can bound the maximum degree of any vertex in some trivial way, and then you can argue that you've thrown out very, very few edges. And so after this process, you get a subgraph that has bounded max degree and has pretty much all the edges of the original graph. So the key observation we use here is that if I look at the degree of a vertex, I can actually write it as a low degree polynomial in the indicator variables that are like saying whether the vertex v appears in the set S. And because S is a random set of size L, those variables essentially behave as independent Bernoulli p variables, where p is L over n. Okay? And then you can apply this Kimvu concentration inequality, which is a concentration inequality for low-degree polynomials where the inputs to the polynomial are these Bernoulli random variables. It turns out this does not work off the shelf. We have to go through their proof again. And it's essentially applying some high moment method, but in the end it does work. And this works provided that L is at least some like log to the 5n. There's some other thing we lose, some log squared loss we lose from this heavy pairs issue, which is actually this thing that Noah was asking about, where this sort of reflexivity property of the hypergraph. And plus the extra log n gives us the extra log n coming from the LDC lower bound gives us this log 8. Okay? And so I can now tell you what Tal's key idea is. If you rephrase it in this probabilistic language, essentially what he argues is that using the second moment method suffices. We didn't need to do this much more complicated higher moment calculation. And in fact, if you just use the simple second moment, you only need L to be log squared. So you can get away with a much smaller value of L. He also shaves off an extra log n from the heavy pairs, although this turns out to be something that was perhaps lost here because we were a little bit sloppy in our proof rather than requiring anything that substantial. But in the end, he gets this very nice log to the 4. Right? So
this is literally using Chebyshev's inequality or something? Instead
yeah,
of,
yeah. Literally use Chebyshev's inequality. Yeah. And so then the final optimization is that if we have a block design, turns out you can actually take L to be log n, although this requires modifying the graph in some non-trivial ways. And I guess if we take L to be log n, it turns out for designs also there are no these heavy pairs, so you don't lose this log. And the only extra log you lose is the extra log coming from the LDC lower bound. That gives you a log squared, which is square root k. So that gives you the optimal thing. Okay. So that's the main technical part of the proof. And I guess let me just conclude the talk by discussing some of the open problems. So the first question you're probably wondering is, what happens for larger queries than just 3? And you can go through this degree heuristic calculation, and what you can see is you can take L to be something like n to the 1 minus 2 over q minus 1. This is better than the L you would take in the LDC lower bound proof, which is n to the 1 minus 2 over q. So it's a little bit better, but it's not substantially better. It's essentially like plugging in q minus 1 into the LDC lower bound. So if you're willing to work a little bit, you can probably prove an LDC lower bound that's like n to the 1 minus 2 over q minus 1 for q-query LCCs. It's a little bit better than the LDC lower bounds we have, but it's not really that much better. So you can also wonder, what do we do for nonlinear codes? That was different. So for nonlinear codes, the decoder can be adaptive, and this is annoying to deal with. And what we do is we form these chains kind of adaptively. We just invoke this decoder and sort of it's kind of I guess the way to view it is like you look at the decoder, it makes 2 queries, and when it goes to make the 3rd query, rather than making the 3rd query, you invoke the decoder for that index, and then you just form a chain like that. And when you form chains, if the success probability is 1 minus epsilon, it goes now down to 1 minus r epsilon. The union bound here seems rather inherent. And in particular, the key point here is we cannot use standard reductions from like Katz and Trevisan, which are some very nice reductions that work for converting nonlinear codes to something that essentially looks like a linear LCC or LDC, but it turns out that that reduction doesn't actually work here. So it doesn't like fit in with this chain derivation strategy. So we had to do something different. And here we need the full power of the spectral refutation and CSP refutation methods. We can't get away with these sort of simpler or potentially simpler combinatorial reductions to 2 LDCs. We really have to use matrix norm bounds. So I want to return to this conjecture that Reed-Muller codes are optimal linear LCCs. And we basically know that this is true. I mean, for designs, it's true up to this 2 root 2 factor, so we almost have it. And for general linear codes, we have it up to this root log k in the exponent. So I think the more interesting open questions are, what can we do for nonlinear? Can we get an exponential lower bound for nonlinear codes? At this point, I actually think I know how to do this. So I think the more interesting question is, can I do it when epsilon is large? So all our lower bounds for nonlinear codes are in the regime where the success probability is 1 minus epsilon. But what happens if the success probability is something like half plus gamma, right? Then the lower bounds are not going to work. And I think the other interesting question is, can we go beyond k cubed for 3 LDCs or 4 LCCs? And here, even if we do linear codes, that would already be very nice. So I think these are by far the 2 most interesting open questions after all this work on this problem. And yeah, this is probably a good place to stop. So thanks for your attention. So yeah, so we can do larger like fields for linear. Actually, Omar and Venkat's proof I think only works over fields of characteristic 2 for some strange reasons. Let's see. The design case has to be for F2 for some. The design case we only have for F2. For, I guess, Omar, yeah, so the design case is only for F2. Omar and Venkat's proof is only for fields of characteristic 2. And then this more general thing like this log, or like the k to the 1/4 will work for not any field, but like fields of like size up to like a k to the little o of 1. There's like some field dependent factor. It's kind of like a delta squared k over field size squared.
You think the field size to be constant?
Yeah, for constant fields, it works just fine. So yeah, I think for nonlinear codes, for nonlinear LCCs, larger alphabet doesn't make much sense because you're sort of saying like, if I read these 3 symbols, can I recover this other symbol? It feels like a little bit weird. They're not really well defined at that point. But for linear codes, it makes perfect sense. So for linear codes, larger fields is pretty valid. Also, all our constructions are linear, so like